So now I would like to invite Kenneth. Hi.
Hi, Kasha. Thanks for
Hi,
having me
welcome on
on.
stage. This is actually a really, really interesting presentation. I've been looking forward to this. So Kenneth is with NSC or New Silicon Corporation, and he'll be telling us about integrated CMOS plus gallium nitride micro displays, all fabricated at wafer scale. So very interesting innovation. And whenever you're ready, please share your slides.
All right. Thank you
And
very much.
we look forward to it.
So thank you
Thank
everyone
you.
for attending my talk today. I'm Ken Lee. I'm a co-founder of NSC, and I'm here to talk to you today about truly integrated CMOS plus GaN microdisplays that can be fabricated at true wafer scale. A little bit of my company, right? We are a spin-off from Singapore MIT Alliance for Research and Technology. That's SMART for short. And SMART is a collaboration between the Massachusetts Institute of Technology from the US and Singapore institutes. So SMART is a research center based in Singapore that is focused on creating technologies that can be translated into commercial realities, right? So in SMART, the program that spun off this company basically focused on semiconductor technologies that can look beyond the Moore's law, traditional Moore's law roadmap. And what we've done in SMART Lease is to create a proprietary CMOS plus 3.5 integration platform. So what we are able to do is integrate compound semiconductors devices, right, with standard silicon CMOS transistors and devices in a monolithic fashion and at full wafer scale using conventional silicon manufacturing infrastructure. And what this will allow us to do is to create chips with advanced functionality and made in a very, very manufacturable and cost-effective way. Why is this important? Well, for microdisplays, you can look at the device density of such chips, right? And if you look at it, microdisplays have as many LEDs in terms of density as some of our relatively recent microprocessors. So what that means is you've got literally millions of transistors and LEDs now with microdisplays to be made in a single chip. And that's why the goal is to use the most advanced manufacturing technology, which is silicon CMOS manufacturing infrastructure, to create all these chips, right? So if you look, for example, your expected AR, VR chips in the near term, expected to have device densities on the order of a couple of million per millimeter squared. And this is really equivalent to some relatively recent CMOS process nodes, right? Transistor densities accessible by those. And so if you use a CMOS manufacturing infrastructure, you basically have a built-in manufacturing capacity that's available and on tap and allows you to scale from product development all the way to full production very, very quickly. So just a little bit about why our technology is different and why it's important. So when it comes to CMOS-based microdisplays, there are generally two ways to do it to bring the 3.5 devices, i.e. the LEDs, into the silicon world. So on one hand, you have line bonding, where you basically have to form your devices in the 3.5s first and on your silicon backplane, and then you have to put them together in an aligned fashion. And then there's what we call direct bonding, where you basically do not have to worry about alignment during a bonding step. So, for example, in aligned bonding, where companies such as Plessey and McLady practice, right? What they do is basically they have two separate chips that are practically fully formed and use things like thermal compression bonding, or they use molecular bonding to bring these two chips together and form electrical contacts with proper alignment. These have challenges in terms of bonding alignment, and generally the key killer is yield and manufacturability, right? So bringing to scale, going from a product demo to real commercially economically viable scale, that's the challenge. In terms of direct bonding, what you have is very typically, well, at least by practice by Jade Bird, right, where they basically form the CMOS interconnects fully, and then they bond blanket GaN, and they fabricate the GaN devices after the bonding. And so this is also this solves the alignment bonding challenge, but there are scalability issues because you need to use new tools, or if you need to build a process line that's catered for this process, right? And you need to basically develop it and put in all the effort to bring the yields up and the costs down. In contrast, we use a form of direct bonding, but we